Good afternoon, everyone. I am Likynti Banri Tiewsoh. Our paper ID is PP27, and the title of our paper is Lattice Filter, Design, Fabrication, and Characterization for Photonic Integrated Circuits, which have also been prepared by Srinivasa Vairao and Subhash C. Aryal. We are from the Lightwave Communication System Laboratory, Department of ECE, NEHU, Shillong, India. Coming to the abstract, here in our paper, we have used 4 unbalanced Mach-Zehnder interferometers to design a 2-stage lattice filter to improve the overall flat-top response. Coming to the introduction, so what is a lattice filter? So a lattice filter is an example of an all-pass filter in which the attenuation is constant at all frequencies, but there is a relative phase shift between the input and the output. So here in our FIR lattice filter, we have used 4 unbalanced MZIs with the value of delta L is equal to 0.264 micrometer, 100.32 micrometer, and 50 micrometer. We have used these values of delta L to get power coupling coefficients of 6.69%, 25%, and 50% respectively. So this has led to a flat-top transfer function with a free spectral range, that is Fsr is equal to lambda square by del L Ng. And as we can see from this figure, so this graph compares the single-stage MZI with a 2-stage filter, and as we can see in a 2-stage, there is a flat-top response. So coming to the experimental, so we have designed this lattice filter in K-layout. So this figure shows the layout of a 2-stage lattice optical filter using Psi-APIC2. And as we can see, we have used 3 fiber grating couplers in which the output or the input is taken. And this box here is the detector. We have used 2 detectors and 1 laser. Also, we have used 5 broadband directional coupler. This is a broadband directional coupler, and there are 5 total in numbers. And these are the 4 unbalanced Mach-Zehnder interferometer. So the difference between the arm length of this first one, it's 0.2644 micrometer, and the value of del L in the second Mach-Zehnder interferometer, it's 100.32 micrometer, and the value of delta L here is 0.106 micrometer, and here it is 50 micrometer. So these are the optical waveguides in which the light is coupled to the optical grating coupler. So we have also designed the second order lattice filter in numerical interconnect. Here, it's an optical network analyzer in which the output or the input is taken. And this one is a broadband directional coupler. As we can see, we have used 5 broadband directional coupler in K-layout. Also, we have used 5 broadband directional coupler in numerical interconnect. So, as we can see, the broadband directional coupler, it is a 2 input port and a 2 output port, in which the output from the broadband directional coupler, it's given to a strip waveguide. So these are the strip waveguides. So we have used a strip waveguide instead of a rip waveguide. There are 2 types of waveguide, a strip waveguide and a rip waveguide. But we have used strip waveguide because it has many advantages, such as it has very low optical loss, 2 to 3 decibel per centimeter, and also it is cost effective. So as we can see, the output is given again to the broadband directional coupler. So this process continue, and the input is taken to the optical network analyzer. Also, this design has been fabricated using electron beam lithography at the University of Washington, USA. Results obtained. So, figure 3, it shows the transmission response graph of or functional device, that is a second order lattice filter. And as we can see, there is more flatness at the top. And figure 4 shows the gain and phase response of a second order lattice filter. And as we can see, the gain is below 0, that is negative, because when light passes through a device, light is absorbed by different components. So we have some losses in a device, that's why it is negative. And this one, it shows the linear response of our second order lattice filter. So also we have a look at the Fsr graph, or the free spectral range. Fsr stands for free spectral range. And from this graph, we can see that at different values of lambda, we get different peak values of Fsr, which means that Fsr is a wavelength dependent. Fsr is defined by lambda square by del L Ng. So del L is equal to L1 minus L2. That is the difference between the two arms of the Mach-Zehnder interferometer, and Ng is the group index. Discussion. This figure shows the Monte Carlo simulation curve of a lattice filter to access the flat top gain variation, and we have run for four simulation runs. And we can see from this graph that there is a high impact on the gain curve because of manufacturing variability, that is the wafer thickness, and feature size variability. Conclusion. So, in the first simulation run, the lattice filter gave results as paired theoretical calculations of Fsr and flat top gain. However, from second to fourth simulation runs, there is a feature size variation, and also there is a significant shift in gain peaks and flat responses. So one should make an effort to reduce the undesirable variability at fabrication tolerance. This can be done by choosing the proper waveguide width from 600 nanometer to 400 nanometer in the basic building block of MZI's in lattice filter. Acknowledgement. We would like to express our gratitude and thanks to Professor Lucas Krastarski for his constant guidance and fabrication facility of lattice filter through the EDX course on silicon photonics design, fabrication, and data analysis. Also, we would like to thank the ANSYS Numerical Incorporation for providing technical support, that is the short-term license to carry out our research work. And finally, we would like to thank all the researchers of the Lightwave Communication System Laboratory Department of ECE NEHU, Shillong, for the support. Thank you.